This is a rig I just made up to start the process of trying to figure out the center of gravity between, or as compared from a Wizzjet chassis to a new Dash Generation 3 chassis. You can kind of see that this is all set up. It's sort of a temporary setup, but I think it's going to work. I got these two tech blocks. They're glued to the table with super glue, and then I've got this common shaft going through everything here that's glued to the blocks. You can see that's it's a long, like 6-inch piece drill blank, and it's common. It's going through both of the chassis right through the front end. You can kind of see how they're sitting there. The cars themselves are set up with basically equal parts. They both have a dash armature in them. They both have RTHO top gears. They both have titanium rear axles. They both have titanium gear shafts. These are complete rolling chassis with one exception. Well, a couple of exceptions. You can see here I shifted the tires. It's got the right number of tires, but the rear tires are shifted, so I can actually just look directly at the axles in comparison at the rear axle. So they're not in exactly the same place up and down here, or towards it in a way, because these two chassis have slightly separate, different centers of gravity. And like I said, it's basically a complete rolling chassis, with the exception of there is no magnets in here. And I'll have to address that separately, because when the magnets were in here, they were interacting with each other enough that it was kind of throwing off the readings. So you'd push on one, and the other chassis would move the other direction because they were repelling each other. So I had to take the magnets out, but otherwise it's a complete chassis. It's even got it's got the motor brushes in there and everything. Common setup and everything like that. These are different color tires, but the hubs are the same, so those rear tires will weigh the same. So you can kind of see they're basically identical setup. I got my microscope up here. It's focused right down on, so you can see the rear axles. Once again, it's the dash chassis on the right and the Wizzjet chassis on the left there. And what I'm going to try to do, and I've got a dial indicator sitting here, and it's got, I've pulled the main spring out of it, but it's still got a coil spring in there, so it's got just a little bit of force to it. So I've got it backed off right now. I just jammed this little piece of test track in there and hold it back so you can kind of see what's going on. It's got a plain, it's got no tip on it on the dial indicators. It's flat. So you'll see that come into play here. And what I'm going to do is I'm going to do multiple readings here, because it's a little tricky. I have to to get everything to settle, I kind of have to rap on the table a little bit and make sure they all kind of settle into position. So I'm going to keep doing that and write the readings down. So basically I'm going to bring the tip in on the dial indicator, and when it touches the first shaft, I'll make a note of the dial indicator reading, and then when it touches the second shaft, I'll make a note of that dial indicator reading. So that's the difference of the projected center of gravity back to the rear axle. I'm going to have to do a little math to determine what the effect that is at the actual center of gravity, and then I'll have to add in the effect of the magnets, knowing how high the magnets are or how low the magnets are in each one of these chassis via separate measurements. So it's kind of a complicated thing, but I think I can get it, a pretty doggone reasonably good answer here using multiple readings. I'll do one reading right here on the video so you can kind of see what's going on. So I let it go, and the spring goes back. You can see what's going on with the piston of the dial indicator. So try to do this with my knee. I'll just bang on the table with my knee a little bit, get everything to kind of situate. Actually, I don't like that. I'm going to bang with my camera, so it's going to be loud. Okay. So you can kind of see the shafts aren't quite aligned with each other. So what I'm going to do here is I'm going to slowly bring that tip in. And when I see that first shaft move, first axle move, okay, starting to move. The reading on the dial indicator is 73. I'm going to move this in until the other shaft moves. There it is. Reading is 69. So there's not much difference there. I'm going to do this again. Okay. Okay. Oh, shit, I went too far. Okay. Do it again. Okay. Trying again. Oops. Why can't I see the... I don't know what's going on here with the screen's kind of messing up on me, but I can see when the shafts are moving. Okay, there it goes. The dial indicator's at 74. There goes the other one. Dial indicator's at 66. Okay, so a difference of 8 thousandths. That's when I've done several of these before I started videotaping, and it's usually about that, somewhere around in that range of about 8 thou difference. So I'm going to do a bunch more of these. I'm going to write the numbers down and then take an average of all those numbers. I'm going to throw out the high and the low, and take 10 readings, throw out the high and the low, and take an average of the rest, and then that'll be the number. Okay, so there's the results. I've got some results here. I did 10 runs, and the highest was a 7 thousandths difference. So you can see the reading I got from the dash chassis. I wrote that down, and then when it hit the Wizzjet, I wrote that down, and then the difference is that number there. I did 10 readings. I threw out the highest one and the lowest. There was only one 7 thou reading, and then there was a bunch of 5s. I threw out one of the 5s and one of the 7s, and then averaged the remaining 8. I got 0.0054. So when I really got down to it, yeah, that looks like it's pretty darn consistent here. I guess when I pre-did it before I started doing the videos, and I was getting, I got a couple of 7s and an 8, I think, before I started doing the video. I think I was banging the table really hard, and it's like it's all over the place when you really hit the table hard. So I think this is right. I'm just kind of wrapping on a table like this to get everything to come in. So I think that's a pretty good number. So now I have to do some math and do a few other inspections, which I'll try and record. So to summarize what we just did in a diagram form, just so it's a little bit clearer, I just made this nice diagram up. So up here, this is the front axle, center line. You can see the wheel there, the front axle, everything's suspended by that. And then down here, this is the rear axle for the two cars. Green is Wizzjet, and the pencil or gray is Dash. Now everything's greatly exaggerated here, so you can kind of see what's going on. But we're coming in here with the dial indicator tip, and we're pushing on the rear axle of the Wizzjet first, and then going until it lines up with the rear axle of the Dash G3 chassis, and that'll tell you the distance, which I'm calling C. This is the vertical center of gravity difference that is projected to the rear axle. So, what good is that? Well, if I know the wheelbase, which is, centerline distance to centerline distance of the axles, and I know the distance from the front axle to the center of gravity in the horizontal direction, in other words, along the axis this way from here to here, then I can use that ratio plus knowing the mass of the car without the magnets in it to determine what the actual center of gravity is right there in the middle, which I'm calling D. So, to cut to the chase a little bit, I made some measurements, and I've determined that the wheelbase for the two cars, Wizzjet is 1.470 as I measured it, 1.474 for the Dash, so almost the same. And then the B distance, which I'll show you how I did that in a second, but the B distance is 768. I mean, these are kind of approximate numbers, but I came up 0.768 and 0.773 respective of the two chassis. Then you take the ratio, and you end up with this. Let me show you how I did the center of gravity. This is the This is the new dash chassis here, but it works the same either way. Well, first of all, you have to find the right block. So what I'm doing is, this is kind of hard to do with one hand, but I'm getting it balanced. So it's balanced right there, you see. It's not falling over as I move it up forward. It falls over as the balance point gets basically right in line with the front of the armature hole. That's basically where that sits. So I'm going to measure the distance from the center line of the axle to the front of the armature hole. When I did that with the Wizzjet chassis, it did the same thing. So it's basically in the same basic spot. I mean, you know, this is some false accuracy, obviously, but you know, I don't know it to a thousandth of an inch, but it's pretty close. And that, you know, for this calculation, as you'll see, it's probably, you know, that's fine. So as we crunch through the numbers here, this is the formula. So D, that's what I'm looking for. That's the actual vertical center of gravity difference between the two cars. That's equal to C, which is the number we just determined from the previous run. That's the distance at the rear axle as we're measuring it. And multiply that times the ratio B over A. So B is the distance from the front axle center line to the center of gravity. And then A is the wheelbase. So basically B over A, you know, the two cars, it's almost the same number. I took an average as 0.523. So the answer here is the 0.0054 value that we got in the previous run times 0.523, which means the difference in the center of gravity of the two rolling chassis without the magnets in it is 0.0028. So now the next step, of course, is, you know, we're going to have to add the magnets back in, which is going to require some more analysis and some math. The next step in the process is we're going to have to determine where the magnets are sitting relative to some known surface. So what I'm doing is lining it up with the axle once again, and I'll describe the setup and the measurement here for you. But right now I have the new dash chassis in here, but what I have is a dial indicator. It's got half a thou increments on it, and I've got the tech block, and it's sitting on a piece of glass. It's the flattest thing I can find, and what I've got is the dial indicator is zeroed. You know, it's pretty close to zero that's about as close as I can manage, touching the top of the tech block. So if I'm, you know, back there at zero, if I move it over here, it's hard to do with one hand, by the way. Move it over here, still zero, well, you know, give or take. Move it over here, zero. It's a half a thousandth low there, but you know, as long as everything's consistent here from one reading or from one car to the next, it's going to work out just fine. So it's basically zero there. So basically what I'm going to do is measure the distance from the bottom of the axles here. These are 065 drill blanks. All the chassis have 065 drill blanks in them, and snug. You know, the holes in the chassis are peened, and so these are snug into each hole. And you know, sitting flat. They're not rocking. They're not three-wheeling. They're sitting flat. I made sure of that. And I've got these magnets. I'm going to use the same magnets on every chassis. Or the same height of magnets on every chassis to take that out of the equation completely too. So what I'm going to do is measure the distance from the surface to the top of the magnets, and I'm just getting I'm going to compare the differences between them. I don't really care what the number is. I'm just comparing the differences between them to determine how high the axle or how high the magnets are relative to the axles. Now you might wonder, you know, why don't you just measure it to the floor of the chassis? That's a good question. Thanks for bringing that up. The reason is the floor of the chassis is not level, and so it's going to depend greatly on where you actually put the dial indicator when you put when you get the reading. So you move it over 1/8 of an inch one way or the other, you're going to get a different reading. That's most prevalent on the dash chassis, by the way, because it's really it's kind of dished out in the middle, there's a pretty big gap, especially in the rear magnet. There's at least like a 7th thou gap, I think, under the magnet in the center. So it's the bottom of the chassis is sitting like this, and the magnet's only touching at the two ends. It's sitting in there like that. So in the middle, there's a gap right through. You can see right through it. See light right under it. So, and I think all chassis are like that. I mean, they're just molded out of plastic, and they do warp a little. So, this tells you where the magnets are actually sitting. So, I'll show you a sample here. That's again kind of hard to do with one finger or with one hand here. Okay, I'm bound 0, and I'm just going to move it over here and set it on the rear magnet. And that is 0.221 inches to the rear magnet on the dash. And then if I move it to the front, it's a little extra hard because I got to remove the magnet. Okay, so then I move it to the front, and bingo, I've got 0.218 inches. So I'm going to do that. I'm going to do this for both the chassis, and I'm also going to, just for grins and giggles, I have a Aurora number 12 chassis here. That's a really good chassis. This is just happens to be the car that Jeff ran in the Frey Individual Championship last year. He finished second. It was also he ran the same car at the Quarrel, where he top qualified. Wizzjets were legal for that, and he ran this Aurora chassis and was the TQ. So it's pretty good. I'm just saying it's a pretty good car. So I'm gonna get the numbers for that car, the Wizzjet, and the dash, and I will present the results as soon as I get them here. All right, the moment you've all been waiting for here. This is the comparison of the magnet heights between the 3 chassis builds. I went through and I did 5 readings with each chassis. As you can see, if you look at the numbers, they're pretty consistent, so it's not changing very much. I think the biggest variation of anything was a 2,000th variation when I did this one here. I'm not exactly sure why, but it's pretty doggone consistent, I gotta say. And then I just tallied them up and took an average. Took an average of the readings. So what we see here is this is the first number is front magnet, and then the slash, and then it's rear magnet. You can read all this gobbledygook when you get, well, I guess I'll read through it. This is magnet height comparison. The front magnet just happens to be 0.234 inches thick. The rear magnet just happens to be 232 inches thick. Nothing magical about those. That's just what they are. So if you wanted to use these numbers and figure out where the bottom of the magnet sits, by all means, go ahead and do that. The distances shown are from the bottom of the axles, as I showed in the previous video, or previous part of the video, and there were 65 drill blanks, to the top of the magnet, measured at the center of the magnet. So, so we'll see here that the average on the dash, it was a 2.218 in the front magnet and 0.220 in the rear magnet. I'm just truncating the last digit, but Wizzjet is 0.2278 front magnet, 0.225 rear magnet. Aurora number 12 chassis sample that I have is a 0.2322 in the front magnet, 0.2300 in the back magnet. So now, I just say that, I mean, this is a number 12 chassis. It's, I guess recognized as one of the best chassis you can use to build a freight car. It sits low, and it's, it's got other nice benefits to it. It's a good chassis. Anyway, so the conclusion you can draw from looking at the number, the Dash G3 magnets sit lower to the track than they do on a Wizzjet by about 0.0096 inches on the front magnet and by about 0.0042 on the rear magnet. The Wizzjet magnets, comparing the Wizzjet to the Aurora number 12 chassis, the Wizzjet magnets sit lower to the track than they do on the sample Aurora 12 chassis by about 0.0044 inches on the front magnet and about 0.0050 inches on the rear magnet. So anyway, that's what I have here. The next step in the process to get the full center of gravity will be to basically add the rolling chassis from before without the magnets in it, plus the magnets, and we'll get an answer there. So that'll be the next portion of the video. I also failed to note that I'm using a different chassis than I was before. I didn't feel like taking these chassis all the way down apart again to put them on drill blanks. I just went ahead and grabbed a different dash chassis and a different Wizzjet chassis. I've got multiples of these, and I went back and spot checked also another one of each, and the numbers came in the same. So I think I can say with reasonable certainty that a Wizzjet chassis is a Wizzjet chassis is a Wizzjet chassis, and a dash chassis is a dash chassis. So I just wanted to point that out. Now, coming to the conclusion of the center of gravity calculation, here's some numbers and math and lots of discussion, so I can read this off. So this is the calculation to get the total center of gravity of the rolling chassis, including the magnets. So basically what you do is you find the weight of the chassis. I weighed the Wizzjet rolling chassis less magnets, and the dash 1306 grams versus 1313 grams. Pretty close to the same answer. I just took an average of the two. The magnets, I weighed them 2.13 grams each. So the method of calculation basically is you take the weight of each individual part, in other words, the rolling chassis less magnets, times its delta in center of gravity, and the magnets one at a time times their delta center of gravity. And then when you get all that summed up, then you divide by the total weight, and that gives you the total difference in the center of gravities. So I know that sounds kind of complicated, but it really isn't all that tough. So here's the math. I got the chassis less magnets is 13.10 grams times minus 0.0028, plus the front magnet is 2.13 grams times minus 0.0096, and the rear magnet is 2.13 grams also times minus 0.0042 inches. So that gets you these numbers, which is 0.0660 gram inches. Gotta put the units there. And then basically you just take that number and you divide by the weight of the car, which is the rolling chassis less the magnets, plus magnet plus magnet. So it's 0.0660 negative divided by 17.36 grams. That equals 0.0038 inches. So the conclusion is the vertical center of gravity on the Dash G3 chassis is 0.0038 lower than that on the Wizzjet.